So let's go ahead and take out series parallel. So this is the part where things get very interesting. So far we've talked about series circuits, which is very easy, right? Because what's the best thing about a series circuit is all things do what? Everything always adds up. Then we went to parallel. What was the hardest part of parallel? Resistors. Having to try and calculate total resistance using the inverse method. Yeah. So this is a combination of both series and parallel circuit paths. You have to be able to identify how the components in the circuit are arranged in series or in parallel. You have to see how so we're looking for what is the relationship between the resistors on the board. Okay? That is the best way I can boil all this down, is how are these related to each other. So in the first case here, so we're coming from our voltage source, we hit one resistor, and that's just one current path, yeah? And then it splits right here at this junction into a pair of parallels. Do y'all see that? So that is why it is series parallel. If I did not have this guy right here in the middle, this junction, this would be a basic series circuit. If I didn't have the blue resistor right here, it would just be a parallel circuit. But in this case, it is a series parallel. Questions? So if you're going to have to find total resistance, you have to figure out how you're going to add these up. Am I adding the inverses? Am I adding the regulars? I'm having to do both. And it's up to you to determine how this has to happen. And that is done by how is it combined? How is everything flowing? Right? Am I just going straight down a river and seeing paths diverge and come back over and over again? That's basically all this is. My path splits, it comes back. Splits, it comes back. So when you're examining this, you have to trace the current flow. So my current is going to be the same all the way through R1, and then it's going to split between R2 and R3 and recombine down here at the other side of R2, R3 and go back. That's how I know that it's going to be series parallel. So the bad thing about this is you have got to pay attention to how you add your resistors. Why? Because if you don't do one right, you're going to basically, it's kind of like playing Jenga. If you don't have the right piece and pull the right piece at the right time, what happens to the tower? It falls, right? Same thing with this. If you don't do the right resistance at the right way, this whole tower can fall, and then your answers do not make sense. Right? So the best way to do this is to redraw the circuit to determine what is in series and what is in parallel, and use that redrawn circuit to determine total resistance. You start at the furthest place from the voltage supply and work your way to the voltage, and redraw the circuit as many times as is necessary to make a very simple circuit. I will not say go down to one resistor. If you can get down to either a series circuit or a parallel circuit, you're good. You don't have to get down to one resistor. Okay? So looking at this guy right here, well, we've already known that this is R1 is in series, R2 and R3 are in parallel, right? So what they do to find the resistance is they know that R2 and R3 are parallel, so they solve for the parallel. Now again, this is the point where I would just say don't go any further. There's no real point to it. All you're going to be doing is giving yourself more work. Because we know what happens in series. They will add. They will add. So R2, R3 plus R1 would end up being 5 kilo ohms, and then you would solve everything from there. They bring it all the way down to a single resistor. Next, like I said, if you absolutely want to, yes, you can do that. But it just means it's an extra step. So I'll kind of leave it up to y'all as to how y'all want to do that. Okay. So let's go ahead and just solve this real quick and see what y'all think about it. So we know we've got 5 kilo ohms total. What is my current total? Huh? So we have 10 milliamps. So what do I bring over here? Am I going to have to distribute voltage, or am I distributing current? We're distributing our current because current does not change in series, right? No, current doesn't change. Current is constant in series. Or are you talking about the one above it? Okay, well, we'll get to that one here in just a minute. I want to finish up with these guys first. All right. So we have 10 milliamps, 3 kilo ohms. What is my voltage? It's 30 volts. Which means that R2 and 3 get what? They get 20 volts. Now those 20, so we now have all the answers for this one. Let's go back up here to our original problem. What am I bringing up here to R2 and R3? What is constant in parallel? Your voltage. So you bring 20 volts here, 20 volts here. Because that is what, okay? We're bringing 20 because 20 is dealing with this particular resistor we created when we combined R2 and R3. Does that make sense? So then we divide 20 by 4 kilo ohms and we get 5 milliamps for our current. Okay? And then you would find power. So what is my power total for this circuit? $500 milliwatts. All right. So R1, what is my power for R1? Now this next part's what you have to really watch out for, because I'm going to end up with 200 milliwatts here. But when I bring it over here, each one of these is going to get what? 20 times 0.005 is 100. Yeah. All right, so the way you would really come to deduct this and check your work so I've got 10 milliamps, and that is my total current. So my current in parallel should add to my 10 milliamps, right? My voltage should add up to 50 volts. So this is what, like I said, you've got to be so careful when trying to verify a lot of this, because this is where your brain's going to start having a freak out meltdown. Because the rules are still the rules, nothing's changed. Ohm's law has not changed. But the way your brain is trying to perceive this means that it says what? I'm not dealing with 50 volts, I'm dealing with what? I'm dealing with 70, because I have two 20s, right? That's when you have to remember to tell your brain, no, these are in parallel. They're supposed to share the same voltage, right? Does that make sense? So then you only need one of those plus the 30 volts. I get 50. Yay, us. So we've talked about current and we've talked about voltage. Let's talk power. This is probably the easiest of it. All right. Yeah, that's the only one you add up all over. But even then, you want to be careful how you do that, because if you add the wrong way, you can end up tripping yourself. All right. Any questions on this, guys? Okay. So I'm going to give y'all just a minute to see if y'all can find total resistance here, and then we'll talk about it. Okay? All right, so what is my resistance total? I hear 40 ohms. Does everybody agree with that? All right, let's verify. So first of all, what do we have to deal with 3 and 5? They're in what? You add them and you get 60 ohms total, right? First of all, you got to find these guys, so that's 30 ohms over here. Then you inverse 30 and 60 to get what? So 20 ohms. That's in series with R1, so 40 ohms overall. That about right, guys? All right. So once you find total resistance, you find total current by just applying Ohm's law. So what did I tell y'all at the beginning of parallel? Is that what does not change? The laws. There are two main laws. What are they? Ohm's law and Watt's law. Thank you. It's Ohm's law and Watt's law. Those laws will not change no matter what you're doing to these resistors. The way we apply them might change just a little bit, but the laws themselves will not change. V will always equal I times R. P will always equal V times I. Those laws do not change. Okay? So we already worked this one all the way out. All right, so I'm going to let y'all work this one for just a minute, and we'll see what y'all can come up with. Okay, so let's talk about answers for this one, guys. Okay? So what you have to do first is we'd already solved for RT. We did that previously with ended up with 40 ohms, yeah? So then you just had to find out what your current total was. I went ahead and found my power total. We're given our voltage total. So you start working back from there. What distributes evenly in series? Current. Current doesn't change. So I bring my 750 to my 20 ohms. And I end up with 15 volts here. I end up with another 15 volts that are going to be distributed between these four resistors. Next thing I do is I know I need to break my current. So I've got 30 ohms total for this run. I've got 60 ohms total for this run. So what I do is I find out, so I ask myself 30 divided by 15, 15 volts divided by 30 ohms should have given you 500 milliamps. Take that 500 milliamps. These two are in series with each other, so you move that between them. Multiply 15 times 0.5, which is 500 milliamps, gives you 7.5 volts. Then, just to finish it off, I went and found power. Ended up being 3.75 watts per resistor. I then looked over here and said 60 ohms with 15 volts, that gives me 250 milliamps. And just start solving for that. Y'all have any questions as to how I got the answers I got? All right, one more. This one you actually do have to start from scratch on.
what we do now is experience, like for like a job or something.
Yes.
Hey, just making sure. I'm sorry, I'm over here trying to watch your job. Sorry.
All right, guys. How far y'all gotten? Y'all got it solved? So you have RT, you have IT, and now we've got PT. We can go in and start solving, right? First of all, I'm going to distribute my current, right? So then I will do 330 times 16.69. That gives me what now? 5.5 volts. What about here at 47? R4. All right, so that leaves what for my combination of R2 and R3? So what is my power at R1? Let's go ahead and knock that out. R4. And my combination here. Okay. So what do I bring into R2 and R3 from this list right here? I'm bringing in the volts. That's 3.72 volts. All right. So then I take 3.72 divided by 680. How much of the current do I get at R2? That means I get what at R3? Okay. So then we look for power last. With R2, what is my power? All right, and R3? Any questions on that, guys? So is it pretty easy, pretty hard? What? So the voltage dividers with resistive loads. So when a load resistor is, that's an oxymoron. When a resistor is connected from the output to ground, the output voltage is reduced. So anytime you add a resistor in to a series circuit, the output voltage is different. So we have what is called a loading effect. So what does that mean? If you take a meter, which a meter has something along the lines of I think it's either a mega ohm or giga ohm, 10 giga ohms of resistance, and you put that in parallel across a circuit, essentially what that does is it drops its own voltage. Now, when we do that with a meter, the resistor is so big you don't even register that it's been added to the circuit when you're measuring for voltage. Unless the resistor is of a similar size, then you really are going to see what is called loading, because the total resistance will drop and your total current will increase and your voltage drop will change because this thing's pulling its own voltage. Does that make sense? So two effects of loading a voltage divider. The load resistor is in parallel with R2, which reduces the resistance from point A to ground and reduces the voltage. The circuit has more current because the resistance of the voltage is reduced because we're putting it in parallel. Does that make sense? So what happens when you place a resistor in parallel? Total resistance does what? Total current does what? Mm-hmm. I'm not going to be so much worried about bipolar voltage dividers. So voltmeters can load a circuit, which we will be doing a meter certification in the next week or two. It's an NC3 certification. You'll get to see the snap-on meters, which are really nice meters. So the circuit can be altered by the internal resistance of a meter. It does so very easily. So if the meter resistance is at least 10 times greater than the resistor you are measuring, the effect is very, very minimal. However, if you put it across a resistor of similar resistance, then you will definitely see some changes. So when a voltmeter is connected to a circuit, its internal resistance appears in parallel with the resistor. This is why you do not put your ammeter in as a voltmeter. It never ends well. An ammeter has no internal resistance. A voltmeter does. Big difference. The resistance from point A to point B is altered by the loading effect. If the meter resistance is much greater than the resistor, then the resistance changes very, very little. But you've seen what happens whenever you add resistors in parallel. That was the last lab you did, right? As you add the resistors in parallel, what happens to total resistance? Is you can actually watch it doing what? You can watch it decreasing, right? As your current is going to be increasing. Okay? So in other words, no, never mind. Excuse me. So electromagnetic or needle type analog meters, the resistance is determined by the sensitivity factor. This can give you a lot of problems with the loading effect. Digital ones, their internal resistance is at the very least a 10 mega ohm resistor, which is a good fair size resistor. So we generally have less problems with loading as to that. That's why a lot of the meters have gone digital more than analog these days, because it handles it much more easily and much more capably. The main reason we would use an analog meter is why? Does anybody have any clue? Not really. They're not really that much cheaper. Or they're really not cheaper at all. Most meters are going to cost a good bit. So with a analog meter, do y'all know what analog is, first of all? It's going to have this needle that swings back and forth. Now, that's great if you want to see a quick changing signal, something like AC power. You can literally watch the sucker bounce back and forth, back and forth, back and forth as it reads the signal. No, AC is a sine wave. So just like the waves at the ocean, right? Or the waves in a wave pool, if you've ever been in one of those. You're still there, but you could be at the bottom of the trough or you can be at the top of the crest. And anywhere in between. Does that make sense? So if you have ever had to deal with a wave, so let's say, let me get a different color. Here's you. I can really not do more than stick figures with this, so sorry. And you're at the beach, and then here's the waves. Where you're standing and what you're looking at is going to depend upon where that wave is in comparison to you. Does it make sense? So with an analog meter, you can see the actual wave. It's one of the coolest things about analog meters is you can actually see the wave as it's happening. A digital meter is just going to sit there and say, okay, so this is the top, this is the bottom, here's in between, this is your average voltage. Because the digital meter is sitting there just doing the calculations for you. He doesn't want to see the tops and the bottoms of the wave. He just wants to give you the steady state voltage. Does that make sense? So it's kind of like whenever somebody's sitting there going, the waves are 5-foot waves. Are all the waves going to be 5 feet? No. It's the average. And that's just what the digital meter's doing, is it's basically saying the average wave size is roughly 120 volts. Or it'll sit there and say, if you have an analog meter, it's sitting there saying, oh, it peaked at, let's say 1,000 volts, and then it dipped all the way down to negative 500 volts. You don't really care about that most of the time, unless you're really got something sensitive you're working with that you need to work to filter out. So that is the difference between DC and AC, is that DC is only one steady state of voltage. Basically, what DC looks like in comparison is it looks like this. And yes, I do mean to do a slash down, because eventually what happens to all batteries? They die. And if you leave them too long, they can crack open and bleed all the acid out of them. Which, that's always fun. Especially when you get it on your skin and it burns. And yes, I am being very sarcastic in the fact that I say that that is fun. I've touched more than my fair share of battery acid. It stinks. It burns, and it really is not a good thing. It's very corrosive. But battery power tapers out over time. The thing about a sine wave, so AC, the difference between AC and DC is AC does not peter out over time. Because I can use things like transformers and capacitors to boost that signal back up to where it needs to be. So basically, if you're talking about the ocean, waves eventually peter off and go flat, right? What causes the waves to stir back up? Because something hits the water, right? Just like in a lake. How does water turn into waves? Somebody comes by on a boat, somebody falls in the water, and all of a sudden you get more waves. Essentially, that's what capacitors and transformers do, is they just basically hit the water a little harder and send the waves on. Does that make sense? DC, we can't really do that very easily. But that wasn't what we were talking about. So we're talking about the internal resistance of a voltmeter. It's generally about a 10 mega ohm resistance, so it gives us less problems with loading. So we also have what's called the Wheatstone bridge. This is mainly used to calibrate sensors. Okay? And I'm going to pause this. So Wheatstone bridge, they consist of 4 resistors, a DC voltage source connected across the top and bottom of the diamond. The output of the voltage is taken from the left and right points of the diamond. So if we go back to the page before, you have your DC voltage source at the top and the bottom, and the voltage reading is taken from the left and right. Make sense? So what these actually do, they're used to help zero out or help work with sensors. So temperature sensors and things like that, it helps zero. This is what you use to zero those out. It's the Wheatstone bridge. So the way we want to do this is we want to balance it out. This occurs when the difference of potential or voltage between the terminals A and B is equal to 0 volts. In other words, when you read the voltage across A and B, that's the 2 outer points, it should read 0 volts to each other. Okay? So the voltages across R1 and R2 are equal, and the voltages across R3 and R4 are equal. So R1 and R2 should be equal, R3 and R4 should be equal. So voltage of 1 over voltage of 3 should equal the voltage of 2 over the voltage of 4. Does that make sense? We won't really be getting too deep into Wheatstone bridges. You mainly do that in, I believe, AC and solid state, James? Wheatstone bridges, so you mainly use them in solid state? Yeah. Yep. You use it mostly for sensors. Yep. So Thevenin circuits are equivalent circuits that behave exactly as the original circuit does. They have the same input resistance and the same output voltage. These circuits only have one resistor and only one source. Again, don't worry too much about this. I don't know where some of this is coming from. Okay. So I don't know where some of that came from, but I'll look at it just a little bit more. So if y'all got any questions on series parallel?